Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all our members to the group and the discussion, and I'd like to encourage us to subscribe and also check our description boxes for other links of other similar videos. And these are going to assist us in trying to comprehend the whole aspect of the concept of electricity and magnetism. So today we're going to look at the concept of capacitors, and this basically is going to cement on the previous discussions that we have done on the concept of electric charge, the concept of capacitors, and how we can describe basically some of the electric circuits which we are going to use an example for today. Now, in this case, for us to understand the concept of charging and discharging, I've given two illustrations on the board on the left and the right, which of course are going to consist of this specific symbol circuit. And of course, we're going to have these two graphs of particularly the concept of current in terms of amperes against time. And then we're going to have charge in terms of farads against time given using this specific initial. And I'm going to elaborate on them, especially when we come across that specific discussion. Now, I'd like us to recall a few concepts which we had learned from our previous videos, which are going to assist us in understanding this specific concept of charging and discharging, and some of the new concepts which we might introduce across or along our discussion. So in this particular case, I mentioned that a capacitor basically is a device that stores electric charge, and we said that it's going to fundamentally consist of a specific structure which is going to be two plates which are going to be oppositely charged for positive and negative. And in the middle here, we're going to have what we refer to as a dielectric, which is an insulating material that protects these two charges from coming into contact, of course, which can result in them being neutralized. So in this particular case, I mentioned that this constitutes the conducting wires, which are going to be at this specific point. And therefore, that one formed a symbol set of what we referred to as this particular device of a capacitor. Now, we had gone ahead and said that, of course, the amount of course, charge which is going to be stored by these specific capacitors can be given a relationship with the potential difference. And we had come up with this specific equation whereby we mentioned that basically this is going to culminate into an equation of charge is equivalent to CV. And we said that C is going to represent capacitance and V is the potential difference being realized from this specific presence of charge. Now, we had said that this charge is going to be measured in terms of farads, and there were different factors which we had considered which are going to affect this specific amount of capacitance being stored in the or being realized by this specific storage device. And therefore, we said that among these factors, there are other cases which we are going to consider, especially for area and the distance of separation of the plates, whereby we give a relationship of capacitance is directly proportional to the area of the plates, and then or the surface area of the plates, and then the distance of separation. And this, of course, gave us a relationship which we had said is going to be given in terms of Ka over D, where K was a permittivity of free space which we had given, and then area is the area of the plates, and this is going to be a distance of separation. Now, our equation culminated into this specific equation which we gave in terms of epsilon naught dE, A over D, and this, of course, was similar, whereby we said that this specific aspect of epsilon naught basically referred to as the concept of permittivity. And this, of course, from our last discussion gave us what we refer to as the concept of this capacitance. Now, in our discussion today, I'm going to look at the aspect of charging and discharging. And as I've said, of course, these two specific illustrations for the right and left are going to give us an illustrative way of trying to understand how this concept of charging and discharging of capacitors going to be taking place. Now, in this case, I'm going to refer this one to as an RC circuit. And an RC circuit basically is a circuit which is going to consist of a power source, a resistor, and a capacitor being given in this specific case. So I can perhaps give it in this summary form so that we are going to follow up it from there. So in this case, a resistor is going to be connected in series with this specific capacitor. So we're going to have this capacitor and a resistor having this specific connection in series. And this is going to be a switch being given at this specific point. So in our consideration, we're going to assume that this specific component which I've mentioned are going to be ideal, in a sense that they are going to be, of course, having this specific components having no internal resistance, especially for the power source which we are going to see at this specific point. And of course, we are going to assume that the connectors, which are the wires being used in this specific instance, are going to be having negligible resistance. Now, in this case, this specific illustration is going to work in a sense that if this particular switch S is going to be closed, the circuit is going to be complete, and the current is going to flow in the clockwise direction as shown by the arrows, of course, in this specific capacitor. But we're going to realize that there's going to be build-up of the opposite charges in this specific case, whereby there's going to be a concentration of the positive charge at this specific plate of the capacitor and the negative charge. And of course, this is going to be gradually accumulating, and therefore going to lead to, of course, the stopping of this specific charge, which is going to be flowing in this particular circuit. Now, this specific point this is going to be making it difficult for the charges to flow, as I said. And of course, the rate of flow of charges in this specific circuit is going to be reduced. Now, in this particular case, this highest point of accumulation, we are going to see that this specific capacitor given as C is going to be fully charged. And therefore, we're going to see that the capacitor is going to be fully charged, and the current, which is going to be given in terms of I. So we can give this one I. It's going to be 0. This is specific point whereby we are going to have a capacitor which is fully charged. We can give that the charge is full in this specific case, but I'm going to elaborate on it at this specific point. We're going to see that this specific instant, when the charge is full, the current is going to be 0, or the current flowing in this specific circuit is going to be 0. And of course, we're going to see that the potential difference, or the voltage across the which across this specific resistor and the capacitor can as well be given in terms of this specific, of course, instance for the flow of current, whereby the charge and the current are going to vary with the time. Now, we can develop particular relationships in order to illustrate these specific cases, whereby we're going to see that we can have this particular relationship of A equivalent to VR plus VC, where this is going to be the sum of the voltage across the resistor and the sum of the voltage across the capacitor given as such. So this is going to be VR for the resistor, or the voltage across the resistor, and then we're going to have a VC as the voltage across the capacitor given as such. So we can describe the total, of course, potential in this specific circuit as the result or the summation of the voltage across the resistor and the, of course, capacitor given as such. And from our previous definitions, we have said that we can give voltage in terms of V is equivalent to IR, whereby the voltage is a product of current and resistance given as such. So therefore, we can relate this particular equation for ours to represent IR, which is voltage across the resistor, and then we're going to have plus voltage across the capacitor being given as such. So from these two specific equations, and therefore we're going to see that we can develop other relationships which are going to assist us evaluate, of course, this specific aspect of current and, of course, voltage whenever we're going to perform our charging and discharging. Hence, as this specific point, we're going to have what we refer to as an instantaneous current, which can basically be found using an evaluation of this specific equation. So as this specific point whereby the capacitor is fully charged, we have said that the current is going to be 0. Therefore, we are going to expect this specific point for the VC, which is going to be the voltage across the capacitor to be 0, since there's not going to be any current which is going to be flowing. So if we are going to have current made as a subject of the formula, we can evaluate this one by having current given in terms. So we're going to use this one. Let me just use this one. So we're going to use this one in terms of, so we're going to have E minus VC R by making, so let's have this, particularly let's have this one as our equation 1, equation 2. So we're going to have our equation 3 given in terms of that specific evaluation for current or an instantaneous current, which I've mentioned. But we have, I've said that this specific point whereby we are going to have the final charge or the charge has accumulated, there will be no of course, flow of current across this capacitor, and therefore we're going to have so whenever we're going to have QF, we're going to have VC equivalent to the current flowing that specific capacitor times the resistance. And of course, we're going to see that arrow given as that one. We're going to see that the current can be defined by making it a subject as VC over R. Therefore, perhaps I can use this particular space. So this will be a continuation of this specific evaluation. So at this particular point of QF, we're going to have the VC given in terms of I times R. But the current at this specific point, as we said, VC over R is equivalent to, of course, 0. And therefore, we can do a evaluation of this specific equation by having this instantaneous current given in terms of E over R, since the second portion of this particular equation is going to disappear. Remember, if we have R as a common factor for the denominator, then therefore we can write this equation in terms of E over R minus VC over R. So the second part, VC over R, is going to be given as 0, and therefore we can have this instantaneous current given in that specific format. Now, the concept of obtaining the current, of course, and the charge can be derived using a specific evaluation, and that is going to involve a concept of a calculus, which is going to be, of course, somehow lengthy, but I'm going to just mention the essential part so that in case we come across it, we're going to do a complete evaluation and try to show how we can represent that specific current. But in case we come across those specific equations, we have mentioned somewhere in some of our videos on the concept of decay curves. So I'm going just to give this specific equation. So we can represent this specific current in terms of this particular is going to be instantaneous current. We can represent it in terms of I naught, whereby I naught is the current at the instant when the switch is closed. And then we're going to have this specific E. We have defined the Euler's number from our previous discussion, so I'm going to have it that way, T over RC given as such. So in this particular case, we're going to have this one as I've mentioned as in instantaneous current, and then we're going to have I naught as the current of the instant at which the switch is closed, and this is of course going to form the maximum current of that specific, of course, instant. And then we're going to have this specific equation being used to derive what we refer to as instantaneous current. So this is going to be the current at the instant at which, or the instantaneous current, whereby this one is going to be the current at which the switches are closed. Now we can graphically represent this specific concept of the current against time using the graph, whereby, as we said, this specific point when the switch is closed, the current will be having a maximum, and then we're going to have it going in that specific case, and it's going to reduce to 0 from this specific case, as we said. And therefore we can graphically represent this particular graph of I naught E minus T. So this is going to be time over RC. So therefore, from the decay curves, we're going to see that the nature of this specific, I hope it's legible from your other end. So therefore, we can consider this a specific graph from this particular point. So suppose we have, like at a particular time t, we're going to see that this specific amount of current is going to be at around T2. But as the time goes by, this current is going to decrease. This is going to be current. So this basically is 2I, which is going to be the current. And then we're going to have this one as 2T. As the time continues to increase, there's going to be a decrease in current using this specific relationship. And that is going to form what we refer to as the graph for charging of the capacitors given as such. So if we try to consider the second case, we're going to look at the concept of a charge against time. But in this, or the charge against time. But in this case, we have said that basically charge is going to be accumulating up to the point whereby the two positively charged, of course, are going to accumulate charge to the maximum. And therefore, we can evaluate that using that specific graph. So at a particular point, at the maximum, we're going to have this particular charge for the Q final, or the final charge, which is going to be indicated using that particular graph. So as well, we can indicate, so I'm assuming these graphs are going to be originating from that specific point, and assuming as time goes by, this particular charge are going to be accumulating in that specific nature, and therefore we're going to have the graph of current against time being indicated using that specific trend as we have shown on the board. Now, in this specific case, then therefore we can as well look at the concept of discharging, or rather the concept of perhaps an evaluation or two, but I cannot do that without just giving an elaboration of this specific formula which I've given on the board. So this specific formula has got a part which I've mentioned for the instantaneous current, and of course the current at of course the time when the switch is closed, which is I naught. So I can as well give this one. I've said that this is going to be given in terms of time for t, but we're going to have this specific aspect of rs, which is going to be the denominator for this particular exponent given as negative t over rc. This is going to form what we call as a time constant, and it's going to be used to determine the time it takes for this specific, of course, device to be fully charged, and of course, or it's going to be used to determine the charging time of this specific capacitor, and of course, the resistor is going to be used, and this is going to be given by this specific concept of RC. So we're going to elaborate on this one, especially on its derivation as they have promised, and of course that's going to assist us to try to measure the time it takes for the capacitor to charge, especially in some of our evaluations using specific examples. So I kind like to request our members to check our description boxes for various links of other videos, and also engage us in the comment section, and also ring that notification bell to be getting updates on our various uploads we do in mathematics and sciences. So don't forget to subscribe, and also kindly ring that notification bell as I've said. So that is it for now, guys. Bye, God bless you. Catch us in our next video.